We are Team2Fast, and for our final project, we chose to complete the Urban Mobility Challenge. Our team members are Allie, Carissa, Haley, Michael, Raphael, and John. Also, we can't forget our race car, Jimmy. The goal of the Urban Mobility Challenge is to autonomously plan and execute a parallel parking maneuver and unpark and exit the parking lot. The algorithm must be able to execute this plan and maneuver while avoiding collisions within the allotted 2 minutes in order to be successful. First, we will give a technical overview of how we implemented the path planning algorithm. The path planner tries to connect the starting pose and the goal pose with a Reed-Shep curve. A Reed-Shep curve is the shortest path that connects 2 points with either straight or fixed radius curves. It permits both forward and backward motion. However, if there is an obstacle, a path is generated using a bidirectional RRT algorithm. The Reed-Shep algorithm returns a discretized array of poses, and the algorithm checks each pose to see if it will collide with an obstacle. This graphic shows how the configuration space changes as the car rotates. The path planner uses this stack of images to check that each pose of the generated trajectory is in a permissible region. Finally, a pruning mechanism is applied that iteratively checks each pose from the goal to see if a simpler Reed-Shep path can connect the starting point to the new point. If it can, it will replace the current path with the new Reed-Shep curve. The algorithm then checks from the new point to the goal pose and iteratively does this process until an ideal path is found. The graphic above shows this pruning process. Now we will talk about the implementation of the peer pursuit algorithm. Given an array of poses that represent the discretized path, the algorithm first finds an associated direction with each pose by checking whether the next path pose is in front or behind the current path pose. If the next path pose is in front, we assign the current path pose with forward direction, and if the next path pose is behind, we assign the current path pose with backwards direction. To find the look-ahead point, we find the index of the closest path pose to the car. We add this index to an arbitrary look-ahead index. In our case, it was 6 indices. The algorithm then finds the necessary curvature to reach the look-ahead point and commands the steering angle of the car. We parse through all the directions and find the cusp poses, the regions in the path that contain a change in direction. The cusp poses are always marked with forward direction. At the cusp, a line is projected from the cusp pose and the look-ahead point slides along this line. Once the car pose is defined to be in front of the cusp pose, the look-ahead point will switch to the new segment. By knowing these cusp poses, we can define each segment to be regions of uninterrupted direction. The old segment is marked complete, and the new segment can be treated as its own path. Lastly, we will talk about our performance and experimental evaluation. We created our own testing environment to be able to test our code outside of simulation. We spent a significant amount of time making visualizations for our algorithms so we could visualize which elements were successful and which elements were breaking down. In this video, the red line is the generated path. The blue square is the look-ahead point. We fed the car a goal pose to parallel park in and another pose to exit the parking lot. The video on the left shows the car autonomously performing these tasks, whereas the video on the right shows the collected RViz simulation results. Thank you for watching how Team2Fast completed the Urban Mobility Challenge for MIT RSS 2018.